Thank you all for coming. It's my pleasure to introduce Boryana Hadzhiyska, and she's probably going to correct my pronunciation in just due course. And she is, just recently joined us from California. She was Miller Fellow over there, and then she did Masters and PhD. So she did a Masters over here. She did a PhD at Princeton, at Harvard, sorry, whereas the undergrad was at Princeton. And she's going to be talking to us a lot about tracing the hidden universe integrated view of baryons. So,
thank you so much. So I actually do have a slide that's an introduction slide with my pronunciation that's coming right after. But yeah, it's a great pleasure to be here. The last time I was here, I was giving a job talk, so it's really nice that this time the stakes are not as high. And so what I will try to convince you in this talk is that studying the gas properties and the distribution of baryons is a worthwhile endeavor that actually holds the key to a lot of very interesting questions, both in cosmology as well as in galaxy formation and evolution. And I do have a self-introduction slide. So yes, the pronunciation of my name is Boryana Hadzhiyska. So it's, I think, easier said than spelled. And originally I come from Bulgaria. As you heard, I did my education mostly in the US, but what I wanted to maybe stress is just kind of how much I changed my interests. Initially, I was very excited about CMB science, and I fell in love with it. And then I came here for a master's degree in part 3 of applied maths, where what I mostly remember from that time was biking for 2 hours every day and doing research with Blake Sherwin on CMB lensing. And then I started my PhD at Harvard with Daniel Eisenstein and Lars Hörnquist. And my focus there was actually on the galaxy halo link. And after that, I decided to go back to studying CMB, which was what I initially fell in love with as an undergraduate student. And so this is also roughly what I'll be talking to you about. It will be this connection between cosmic microwave background, or CMB, and large-scale structure. And in particular, the link between these fields in terms of gas or baryonic physics. And so the main reason that we study baryonic or gas physics is actually because it holds the key to understanding both things about the early universe as well as things about the late universe. For example, by tracing the diffuse hydrogen in the early universe, we can actually understand cosmic reionization, which is the epoch during which the first stars and galaxies ionize the intergalactic medium. And then in the late universe, we are very interested in how gas fuels star formation, cools and condenses, and then finally is expelled from galaxies in powerful feedback processes such as supernovae and AGN feedback, supernovae explosions and AGN activity. And this final point of how the gas is distributed in the universe is actually really, really important for us also in cosmology. The reason being that when doing weak lensing studies, we really need to know how the gas is distributed relative to the dark matter, because knowing that connection gives us a way of doing precision science and extracting the cosmological parameters, as well as understanding the nature of dark matter, dark energy, and inflationary physics. And so this talk will mostly focus on the late universe, which is why I will be not talking about things like the 21 centimeter line, but I do have interest in that. So if you want to chat about this at some point, I'm very excited. And so in the late universe, what are some of the ways in which we can measure the gas? So I call this talk the hidden treasures of the universe, because actually measuring gas is not as straightforward. In fact, there are traditional ways of doing so. For example, X-rays, and X-rays are able to trace the gas in the sort of centers that are very hot of galaxy groups and clusters, and they have a sensitivity that is both to the gas density, which might be what we're after if we're interested in things like in things like weak lensing. And also, there is a dependence on the cooling rate, or which might depend on the metallicity and the temperature as well. And then we have CMB-based probes, such as the kinematic Sunyaev-Zel'dovich effect, the thermal Sunyaev-Zel'dovich effect, and patchy screening. And all of these have, so the KSZ and patchy screening are both sensitive to the gas density, whereas the thermal SZ effect has, even though it has higher signal to noise, it's easier to measure, it actually has a dependence on the temperature, which makes it a little bit more tricky. And patchy screening is slightly lower, is lower significance measure. So that leaves us also with the other promising alternatives of FRBs, or fast radio bursts, which are sensitive to the gas density, and also absorption and emission lines, which have a sensitivity also on the metallicity. So basically what I'm trying to paint right now to you as a picture is that we do have quite a few probes that are sensitive to baryons, but actually quite a few of them also have dependencies on other things, not just gas density, but also temperature and metallicity. And also the significance of these measurements varies vastly. So currently the highest significance measurements of the gas density directly come from the kinematic Sunyaev-Zel'dovich effect. And this is what I'll start with by just as a case study. So the kinematic Sunyaev-Zel'dovich effect results from interactions between CMB photons and free electrons surrounding galaxy groups and clusters. What happens is we have CMB photons coming from the early universe that are then scattering off of free electrons that are moving with some kind of bulk velocity towards or away from the observer, and that leaves characteristic signatures on the CMB map itself. And this is a very exaggerated way of showing this. So if we have a cluster moving towards us, that might leave a hot spot in the CMB, and if we have a cluster moving away from us, that would leave a cold spot. And so mathematically, we can represent that as shown on the left. So the effect on the CMB of this kinematic Sunyaev-Zel'dovich effect, or KSZ for short, is that we get an increment or a decrement on the temperature map, which is proportional to the product of the optical depth and the velocity, the bulk velocity. And so this is exciting because it kind of ties together astrophysics and cosmology. Let me say just what is the optical depth. So the optical depth is the integral along the line of sight of the gas density. And as such, it is a very rich probe of the gas distribution. And then the halo velocity is very rich in terms of its cosmological significance, but it turns out that currently our knowledge of the optical depth is actually much worse than our knowledge of the cosmological parameters, and as such, we always have a direct degeneracy between these two quantities. So then we can turn around this problem and ask ourselves, can we actually learn something about the gas density or the distribution of gas in the universe, knowing cosmology or having some observations of cosmology? So how do we do that? We need two ingredients. So the first one is the halo velocity that we can get from a galaxy distribution, and I will shortly explain how. And then also we need a map of the CMB temperature. And what's really nice about this KSZ effect is that because it changes signs depending on whether we have a cluster moving towards or away from us, that actually ends up canceling a lot of contaminants such as dust that will typically be something to worry about when doing cross-correlation analyses. And so the nice thing is that we can now put together these two ingredients and infer the gas density. So let's go into a little bit of detail about these two ingredients. So the first one is galaxy surveys. So galaxy surveys, specifically spectroscopic galaxy surveys, are huge data sets comprising of millions upon millions of galaxies for which we have their three-dimensional positions. That allows us to get a 3D map of the universe and try to tie it in with our underlying physics to understand dark matter, dark energy, etc. This specific fly-through that I showed you uses the dark energy spectroscopic instrument real data. And this is also the data set that I use for a lot of my work. So the Dark Energy Spectroscopic Instrument, or DESI for short, is currently the largest spectroscopic survey. It comprises of more than 20 million galaxies, galaxy spectra, so three-dimensional information for these galaxies is available, and this is more than any of the previous spectroscopic surveys combined. For this particular study that I will talk about in this talk, we focus on the luminous red galaxies, which are the most massive of the tracers that DESI studies. And for them specifically, we have about 8 million objects, which is almost a factor of 10 better than the previous best survey, SDSS. And so what can we do with this galaxy survey? What we do is we use the continuity equation in order to obtain the halo velocity. So if you remember in the KSZ equation, we have the optical depth and the halo velocity. And so we can use the galaxy positions to solve the continuity equation at the location of these galaxies and obtain a measurement of the halo velocities. And so this is what I'm showing here in practice in a simulation. So if we have the velocity field shown here in RA and DEC, and on the right-hand side here, we have the reconstruction obtained from just applying the continuity equation. And mathematically, the two are correlated at about 60 to 70%. So this is what we roughly expect for an experiment such as DESI, using just the continuity equation. Okay, and then the second ingredient here is the CMB survey. In our case, we use the Atacama Cosmology Telescope data, or ACT. The reason we use ACT rather than Planck, even though Planck covers the entire sky, is that Planck has lower resolution compared with ACT. And if we are looking for these very, very small effects at these very, very small scales, we really need high resolution experiments. So I can just go between the two, and you can see the difference here. So with ACT, we cannot really resolve these small clusters, whereas with, other way around, with Planck, we can't resolve them, whereas with ACT, you can see by eye some of the brighter TSZ clusters, for example, shown in blue. Okay, so now that we have these two ingredients already set up, we can put them together and obtain basically the measurement of the optical depth that we were after all along. The way we do that is by writing an estimator that essentially combines cutouts of the CMB map with our reconstructed velocities. So this is this equation here shown on the left, and the details of it don't really matter. What I'm trying to show here is that it's a pretty simple, kind of straightforward way of measuring the optical depth. So the quantity here on the left is going to be proportional to the optical depth. And essentially we make cutouts. So this T here is the temperature measurements around each galaxy, the velocity around each galaxy, and then we simply sum over all of them. This gives us these kinds of maps here shown on the right. And you can see by eye that we do detect something in the middle, and that something is the optical depth. So how do we make sense of these kinds of gas observations? I wanted to give you a flavor of that as well, because I am interested in the observations, but I'm also interested in the interpretation, which is quite tricky. And there are a few different ways that people have tried to do this. For example, there are things like analytical methods, such as the halo model. And for these methods, you don't really need much computational power. All you need is to make some approximations about how galaxies and gas are connected with the underlying dark matter, and then just create a framework based on this. What is nice about these halo model-based methods is that they're quite efficient. They don't require any simulations, and they're physically motivated. So we know that galaxies live in dark matter halos, roughly speaking, and that's a nice place to start from. And then the cons of these kinds of methods are that they can often ignore important effects, such as, for example, nonlinear evolution of structure, as well as the galaxy bias, so the details of how galaxies are related to the underlying dark matter. And then there is also another way of approaching things is using hydrodynamical simulations. And the pros of these kinds of simulations are that they are the most accurate current representation that we have of the gas physics in the universe. But then the issue is that if we want to study the effect on larger scales, which is what we care about a lot of times in cosmology, we really need to simulate big boxes. But the issue with these bigger boxes is twofold, I guess. One is that we can't really go to very, very large boxes without paying a very hefty price computationally. And secondly, and also as a result, we can't really change the cosmological model, the underlying cosmological model, without, again, paying the price of running a lot of these simulations. And secondly, if we're interested in larger scales, we need to make assumptions about what happens at subgrid scales, which is to say at scales that are hard to resolve with your simulation. So you basically are, you need to make some assumptions, and yet this is currently our best model for gas physics. Okay, and then there is also n-body simulations, and I spent a lot of my PhD work on developing the Abacus Summit simulation suite. So the pros of these kinds of simulations are that they're very large in volume and they're relatively cheap to run. And also they give you access to nonlinear physics, which is typically what's really hard to get by just pen and paper calculations. But then the cons are that all they simulate is gravitational dynamics, so you don't really know anything about the galaxies or the gas. So you need to make some kind of assumption about how galaxies populate these simulations or how they populate the dark matter halos, and also how the gas is connected with that underlying dark matter. Okay, so this was how much I wanted to give you as a sort of like background to what to this field that I'm currently working on. And now I want to spend the rest of the talk in sort of going over where we currently stand and what the remaining challenges are. So currently, so I'm just gonna introduce some of the people in the team here. So there are people from both SLAC and also UC Berkeley. Bernie Reed-Gochaya, who is a PhD student at Stanford, Henry Liu, who is a PhD student at Berkeley, and then myself, who started out as a postdoc there, and now I'm here. Then Emmanuel Shan, who is at SLAC, and Simone Ferraro, also at Berkeley Lab. And so what did we do over the last few years? We've basically been able to start on this journey of creating an integrated view of the baryons. And the way that we've done this is by basically making measurements of these different gas properties on the same sample of galaxies in different frequencies and using different probes. So for example, here I'm showing 6 different types of measurements that are coming from the KSZ in the top left, and then the TSZ, the top 2 on the right, and then a measurement again of the KSZ effect aligned with filaments, which I removed the slides for, but if I have time, I will get back to that one. And then also observations of the same galaxy stacks using X-rays and also using CMB lensing. So why do we do that? Why do we make all of these measurements of the same set of galaxies using different observations? The reason is that they all bring us a different piece of the puzzle. For example, KSZ will give us the piece that gives us information about the gas density, and then TSZ will give us the thermal pressure, and then X-rays will give us the combination of gas and temperature, and CMB lensing will give us the total mass. And so having all of that for the same set of galaxies gives us a way of actually solving the thermodynamical equations and understanding in detail what kind of processes are these galaxies undergoing. So for example, how much inflow is there, how much outflow is there, how far are the baryons being pushed out, and as a result, how much should we worry about this when modeling weak lensing for cosmological purposes? So this is what I'm actually really excited about, and I want to give you a flavor of the different kinds of measurements that we've made. And again, if there is time, maybe I'll include back some of the stuff that I removed. But let's start with the gas density through the KSZ. We already talked about this briefly, but but the KSZ gives us a way of measuring the gas density because it's proportional to the optical depth. And so what I showed you before were these kinds of stacked images of DESI LRGs. And so what do we do having those? So first of all, maybe I should just mention very quickly that, the particular measurement that I will be talking about shortly, uses 7 million LRGs, so there are quite a few of them, with a mean redshift of about 0.7. And it's currently, and that will change very shortly, the highest signal-to-noise measurement of the KSZ effect of about 13 sigma. And so what can we do having these kinds of nice cutouts around galaxies? So one thing we can do is and maybe I should have just taken a step back. So one thing we can do is we can do radial averages from the center of these stacked images. So essentially we can just do radial averages in radius going outwards and turn those into one-dimensional profiles. And this is what's shown on the plot here on the right. And okay, and now I want to maybe take some time to kind of introduce this plot before becoming too excited about my final statement about it. So on the y-axis of this plot, I'm showing the cumulative gas profiles. So this is what the KSZ gives us. You might ask, why are we showing you cumulative gas profiles? This has to do with the details of how the primary CMB needs to cancel out. And so if you show cumulative gas profiles, that actually is better in terms of your noise properties compared with showing the gas profiles themselves. And then on the x-axis, we're showing the distance from the center of these stacked galaxies from DESI. So the units here are arc minutes, and then the units on the y-axis on the right, we're showing optical depth. So basically integral of gas density. And then the next thing I want to show you, I want to state here is that we have the red measurements here that are coming from the data, and all of the other curves that I'll show you are actually coming from simulations. So how do we interpret these kinds of curves that are showing cumulative gas profiles? Essentially what we say is, well, right here at around 2 arc minutes lies the virial radius of a halo of the typical size of DESI luminous red galaxies. And so around that scale, we expect to start encompassing the gas more and more fully. And indeed, once you go to maybe 3 times that virial radius, you see that, that the curve starts to flatten out. That's because we have encompassed the majority of this gas, and there is no more gas as we expand further and further out. Okay, and then what am I showing here? So the first thing I want to draw your attention to is what this would look like, and this is taken from simulations again, if the gas was actually tracing the dark matter directly, rather than being pushed out by energetic processes such as AGN and supernovae feedback. So this is this dotted line here, and you can see that there is a pretty large gap between them, especially at the virial radius. So whereas the dark matter, or the sort of total mass of the galaxy group and cluster, is more or less enclosed within the virial radius, as one might expect, this doesn't seem to be the case for the gas. So the gas appears to be lower than the dark matter curve by almost 50%. So this is a statement of that can be roughly interpreted as saying that a lot of the gas has been expelled, roughly half of it, outside of the virial radius. Okay, and now what about the other 2 curves? So there is the dashed blue curve, which is showing the what the prediction of this line looks like from the illustrious TNG hydrodynamical simulation, and then the dashed dotted line shows us a prediction from the old illustrious simulation. And so what I'm hoping for you to see here is that the comparison between the blue and red is quite different. So the TNG simulation appears to be to have weaker feedback compared with what we see in the universe. And so that was initially a statement that was met with a lot of skepticism, and that's completely understandable, especially given the fact that Illustris 1, the simulation, the green simulation that appears to be in better agreement, has actually been shown to have pretty large problems compared with observations, whereas Illustris TNG was in pretty good agreement with observations up until this point. And so my statement here is that, well, it's very hard to measure gas, and these are the first kinds of measurements that we have of gas properties at these mass scales. So Illustris TNG was calibrated to higher mass objects, and therefore it actually seems to not necessarily, doesn't have to match the lower mass objects that we see here. Okay, so this was sort of one of the first things that we saw in pointing at the presence of large baryonic feedback. However, I want to state that there have been numerous other studies that have also been showing similar results, and I'm listing some of them below, but I will also go to some of the other evidence that we have also gathered over the last couple of years. So one of them comes from the combination between the gas density and mass, which is inferred from CMB lensing. And so while in the previous, let me just take a step back. So while in the previous comparison that I was showing you, we were comparing data with simulations, what I'll show you next actually vastly doesn't depend on simulations. It's an empirical comparison between the mass profiles and the gas profiles. So, okay, so what is CMB lensing? CMB lensing is the results from the deflection of CMB photons on their way towards us, and it leaves very, very strong signatures on the CMB map, which we can use to reconstruct the integrated gravitational potentials. So this is this quantity kappa here that I will interchangeably be calling the gravitational potential, or it's the convergence field if we're being more accurate. So if we make a measurement of the stacks around these DESI luminous red galaxies using the latest maps from ACT DR6, we actually get a pretty strong signature shown here. So this is around 30 sigma measurement of just the CMB lensing stacks. And this is really, really nice because these CMB lensing stacks give us a direct way of probing the total matter distribution. And so similarly to how we were treating the gas density before, we can now take these kinds of two-dimensional maps and look at the 1D profiles. And this is what we did in a recent study where we looked at the luminous red galaxies, two different types of luminous red galaxies, and also a lower mass sample. And looking at all of these, you can see that we have a pretty strong measurement of the total mass profiles around these galaxies. So now we can take these kinds of matter profiles and put them together alongside our gas profiles. And one way to show that is actually by taking the ratio, because the ratio of the gas profiles and the matter profiles gives us the gas fraction, which is one of these quantities that we're trying to understand. How is gas distributed around galaxies going out to a few times their virial radius? And so this is what I'm showing here on the right-hand side. This is the ratio between the KSZ and the CMB lensing, which is roughly the gas fraction, and shown as a function of the distance from the center. And here, the blue dots here show us what the data prefers, whereas the black curve here shows us, again, this Illustris TNG simulation that I already showed you before. And what's really exciting here is to see that on large scales, first of all, we see that this ratio converges to 1, which actually corresponds to the cosmic baryon fraction. So indeed, on sufficiently large scales, we see that the gas traces the dark matter. So this is this is what we expect from first principles. However, on smaller scales, we see that there is a deviation between those. And in fact, at the smallest scales here, shown here at around the virial radius, we see that the gas fraction is roughly 20%, which is very low. And that compared with TNG is in disagreement at about 4 or 5 sigma. And so this was a really kind of exciting thing for us to see once again, that this statement about large feedback that we saw previously when looking at simulations compared with observations can be confirmed once again by just using gas and CMB lensing. Okay, now I want to move on to the other probe here, which is the thermal Sunyaev-Zel'dovich effect. This is work led by Henry Liu, who is a PhD student at Berkeley. And what he did was essentially he took the CMB temperature maps and extracted the Y-Compton signal, which is essentially the TSZ signal. And then he performed stacking using, again, the DESI luminous red galaxy sample. And he obtained these kinds of two-dimensional stacks shown here on the left. So you will maybe notice that these stacks look a lot cleaner than what I was showing you previously. That's because the TSZ effect has a stronger, has a stronger signature. So the significance of these measurements is actually much higher. However, the interpretation is not as easy because we have to now worry also about the temperature of the gas. And so on the right-hand side here, I'm showing the one-dimensional profile shown in orange, compared with, again, this illustrious TNG simulation. And the reason that I'm choosing the same simulation is because in that way you can sort of see how all of these probes seem to be pointing at the same discrepancy between the observations and the simulation. And in particular, in this case as well, because we're showing the cumulative gas pressure profiles, you will notice that the profiles measured in the data are more extended. Or in other words, we see that the gas pressure actually is, seems to have a higher gas times temperature out to very large radii. So this is another kind of piece of evidence pointing towards the evidence for larger feedback. I will say that this measurement in particular has not really been interpreted a lot in simulations and also in analytical methods. And this is the subject of one of the works of one of the master students that I'm advising this term is actually the comparison between the more detailed comparison between these observations and simulations and analytical models. Okay, and so the last one that I want to mention to you is X-rays. And so this work is led by Garrett, who is a PhD student here and now is at Berkeley Lab. And what he did was he took the Erosita maps. So Erosita is an X-ray telescope that has gathered a lot of data, half of which we have access to. And he was able to construct these kinds of stacked count rates. So this is shown here on the left. And you can see that, again, the significance here with X-rays is much, much higher than what we saw with KSZ and higher yet than what we saw with TSZ. But that, again, comes at the cost of the interpretation being more challenging. So what X-rays are roughly sensitive to is the squared gas density times the cooling function, which can roughly be approximated to being the squared gas density times the square root of the temperature. However, there are many more subtleties than what I'm saying here. And I'll mention some of these. So what Garrett had to do was, for example, mask very, very bright X-ray point sources, which would otherwise dominate the signal and also confuse it. He also chose a sort of softer band in the Erosita measurements and was able to extract this kind of signal at an SNR of 172, which is much, much, much higher than the mere 10 sigma that we see in KSZ, for example. And so we then had the thought of, okay, let's see if we can put all of these things together, the KSZ, the TSZ, and also X-rays, and whether that can make sense. Oh, and sorry, before that, I'll just show you what the profiles look like. Okay, so we then thought, let's put all of them together. And we created this kind of plot. So this is all done using luminous red galaxies at mean redshift of 0.5. And you can see the measurements of the KSZ, the TSZ, and also the X-rays. And so we thought, okay, empirically, if we are to believe what these empirical relations say, then we can simply take the KSZ and call that our gas density. Then we can take the TSZ and divide it by, and take the ratio of the TSZ and the KSZ. That will give us our temperature. And finally, take the square root of that and multiply it by the KSZ signal squared, and that will give us a model for the X-ray. So that seemed very naive, but we decided to try it. And here's what we found. So this is still preliminary work, but the model is shown in black here. The measurements are shown in blue. And you can see that this very, very naive model actually does go through the points pretty well. So this was really kind of nice and reassuring. But of course, the details of that are still things that we're trying to work out. So we still need to have a physics model that actually can predict these kinds of measurements all from first principles. And also, we need to study what are the implications for cosmology and specifically weak lensing science. It's also really exciting to me because if we really can do this kind of science with by using X-rays, that can really be transformative to our field because the X-ray sensitivity and significance is much, much higher than all of these other probes that I mentioned before. Okay, so I think I want to say now a few words about the points that are still missing in our model. And what I'm currently working on and what I'm currently excited about. So I'm both excited from the perspective of doing more observational work and taking more taking more data. And on the data side, for example, we're currently working on extending these measurements to lower mass galaxies. So for example, a lot of our work was focused on luminous red galaxies, but we're now looking at emission line galaxies, which are bluer galaxies that are much, much, much less massive. And therefore, it's very interesting to know whether the feedback around them is much stronger or weaker or what exactly is happening. Naively, we expect the feedback to be even stronger there because their potential wells are more shallow. But this is still something that we are currently working on. In fact, hopefully there will be a result in the next couple of months on this. And we're also interested not only on the low mass end, but also on the very high mass end, and focusing more on clusters. Clusters are traditionally where, for example, a lot of the X-ray studies were done on, but in our particular case, KSZ, for example, and TSZ have not really been studied for clusters much. So this is work that I'm really excited about generally, because that would give us a leverage arm, not only across redshift, which is what we currently have, but also across mass. And if we want to understand the effect on lensing, we need to have that full leverage arm across both redshift and mass. And also the combination of these things also with X-rays, I'm, as I mentioned, quite excited about, and the challenges that will come with that. And then in the future, I am also have started looking into this other very exciting thing for me, which is if we do a cross correlation between the absorption lines in the galaxy spectra and also some foreground objects. So just to maybe take a step back here, because I don't really have a slide explaining this one, the idea is that we have some foreground galaxies that have that are sitting between us and a background galaxy. And the background galaxy has some spectrum, and that spectrum will get absorbed by the foreground galaxy, so at specific frequencies. And studying the absorption lines as a function of impact parameter from the foreground galaxy will also give us a sense of the gas distribution and specifically the distribution of different metals and different metal lines. So this is something that we're currently looking into with DESI data, and we're seeing some promising results as well. And then fast radio bursts are the other probe that is very, very sensitive to gas density. The sort of the con is that it requires us to be able to localize where these FRBs are located. So we're currently kind of doing forecasts of what we can do with non-localized FRBs, what we can do with localized FRBs, how many of these FRBs do we need to detect in order to actually beat down, for example, the significance of our measurements with KSZ. And that's kind of also ongoing work at the moment. And then on the modeling side, I think that all of these measurements are very cool, but I think if we can't interpret them, that's not as wonderful. So I'm really excited about finding different ways of painting gas properties and also extending this to different cosmologies. And this is work that we are currently doing with postdoc Lourdes Ondaro and also two master students, Fedir Borejko and Alicia Brezovska. That was my attempt at pronunciation. Okay, and so what we're hoping to do there is basically be able to paint gas properties on n-body simulations and then do some of the analysis to understand specifically these astrophysical questions. And eventually, we also want to bring in other observables. So we already talked about bringing in CMB lensing into the picture, but there is also galaxy lensing that is particularly helpful at lower redshifts, and also galaxy clustering, which can help break the degeneracy between the galaxy halo parameters and the gas parameters. And this is also work that I'm excited to do in the next couple of years. Yeah, so, okay. I do have a few more minutes. I have a conclusion slide, but I was wondering if I can show you very quickly this filament fun project that I decided to spare you this morning. So, okay, I'll just maybe, oops, sorry. Okay, so before I go to conclusions, I want to show you what that looks like. So, okay, let me. Okay, so this project was a project that I kind of did for fun, and I didn't expect to see anything, and was kind of surprised by the results. So, the goal of this, and again, I'll go back one step. So the goal of this was to basically take the galaxy distribution and identify the filaments in that galaxy distribution, and then try to see if the KSZ signal that we're seeing is aligned with those filaments that we have identified. And so the way I approached this was by essentially building a two-dimensional map of the galaxies and then computing the tidal tensor on this two-dimensional map, and then computing which is computed as the Hessian of the gravitational potential, and then diagonalizing that at the location of each pixel to obtain eigenvalues. These eigenvalues give us a sense of where we have the strongest contraction and extension happening due to gravitational forces. And then once having identified these kinds of really beautiful structures, we can go ahead and create this kind of filament map. So the filament map is just telling us if you have a galaxy located in any of these points, then what is the direction of the closest filament, essentially. And so that gave us this kind of map here. And then what we did was, when performing the stacking that I showed you many times before, we just rotated the stacks to be along those filaments. So the filaments are going to be in the horizontal direction. And we obtained this kind of plot here on the left. So, you know, it might not seem like much, but this is actually about a 4 sigma detection of some alignment between the gas and the filaments. And it's kind of exciting because it can give us a way of also understanding the directionality of the expulsion of gas. For example, our AGN feedback correlated in some way with these large-scale structures, or is it actually independent of them? And to actually answer that question in detail, you do need to do very, very good simulation-based modeling here. And I will admit that the simulation-based model that we did in this initial paper was not the most thorough, but it did give us some idea of the discrepancy that we see with these simulations and our measurements. But I'm excited to follow up on this soon. Okay, so I will go now to the conclusion slide and just just kind of summarize what all of these things that I said were. So one thing that I've been very excited about is that we can take the same sample of galaxies and make multiple measurements of different gas quantities, and that this can inform us about both gas physics and also about cosmology. So in particular, I showed you plots of the gas profiles around DESI luminous red galaxies, of the kinematic Sunyaev-Zel'dovich effect, thermal SZ effect, patchy, I didn't show you the patchy screening one, but we also have that one, CMB lensing and X-rays. And they all give us some slightly different information that can allow us to solve for different thermodynamical properties. We found also that these probes are empirically consistent with each other and that they all seem to be pointing at some evidence for large baryonic feedback. This large baryonic feedback would translate into some difficulties in performing weak lensing studies. Why is that the case? Because if the gas were to follow the dark matter completely, then we don't need to, then our weak lensing models can purely rely on n-body simulations or completely ignore gas effects. But knowing that there is a pretty large discrepancy between those two can actually cause a lot of issues and bias our results, cosmologically speaking. So this is exciting in that sense. And currently we're trying to model and jointly analyze all of these different observations to constrain both the cosmological parameters and also understand galaxy evolution. And I'm really, really excited to be doing this kind of work, and I'm very open to chat with students or postdocs who are interested in this kind of science. And yeah, I will leave you with this, and yeah, please ask me any questions. Thank you.